Okay, on your TM1638 board, you have push buttons. Most likely you only have 8 push buttons, but the controller chip can handle up to 16 buttons. So if you supplied your own board, who knows how many buttons it has on it, the controller reads 4 rows of multiplexed buttons. So when you request a read of the buttons, the controller will return 4 bytes. It gives this data in similar format to the other instructions and data. The strobe goes low. You send an instruction with a shift register. That instruction is followed by the data bytes, and then the strobe goes high. Now there's one significant difference. The controller is now sending data on the DIO line, not receiving it. Now on our Hitachi boards, we controlled the direction of the data lines using the read-write line. If we held the RW line low, we were writing to the board. If we held the RW line high, we were reading the board. On the TM1638, the data direction is not switched by a control line, but through instructions by the controller itself. Now there is only one instruction that causes it to switch direction on the digital input-output line, and that's hex 4242, the instruction to read the push buttons. So the moment the instruction 42 is received, the TM1638 switches the digital input-output line to output and uses a shift out register to send the 4 bytes from the keyboard matrix. Now once those bytes are set, the controller then switches the DIO line back to input. Obviously, we have to switch modes on our Arduino digital input-output pin. We were using it as an output, so we got to switch from output to input, receive the 4 bytes using a shift in register, and then set the Arduino's digital input-output line back to output again. But on page 2 of the datasheet, we read, note, DIO output data is N-pipe open drain output when read key demand connect 1K to 10K rising resistance. We promote 10K rising resistance. The read data is unsteady during DIO control end pipe action at the falling edge of shift close. You would refer to below chart 6. The data is steady during rising edge. And if you look at the pretty drawing, you start to get the meaning of the Chinglish. So basically what they're saying is you need a pull-up resistor. Here it is. On the DIO line, when you are receiving data on it. The reason being is they use a MOSFET on the output, which has such a high resistance when it's off that the DIO line will be like a floating wire. And you remember what floating wires did on our very high input impedance digital inputs, right? They were so sensitive that they would pick up induced electrical noise. So by putting on a 10K pull-up resistor, the wire is no longer floating, but held high to get rid of erroneous signals. Conveniently, on both the PIC and Arduino, we have the option of using internal pull-up resistors, which happen to be around the 10K value. Perfect. So when we switch our designated data line on the Arduino from output to input, we will use the input pull-up instruction. Now, I have sample code in the download section if you like. We set up everything the way we did before, and if you want to leave your display off, you can. I did, but it doesn't matter. We then set the strobe to low to send an instruction, which is hex 42. Notice we do not set the strobe line high after this instruction. The controller immediately switches the DIO line to output when it gets that instruction. So we change the Arduino's data line to input pull-up. grab the 4 bytes with 4 shift-in instructions. And you can see I called my bytes keys 1 through 4. Once the 4 bytes are received, I switch the Arduino digital input-output line back to output and set the strobe line high. We are all set up again, ready to send more instructions. Now, in my sketch, I set up serial communication, and in the loop function, I send an identifier for each byte, and then the number that was actually in the byte. I put a line return on the last number, so the next batch of numbers will be on a separate line. I take just a teensy-weensy break, then loop back and do it all over again. Now, when I flash my Arduino, I run the serial monitor, and now I get a live action feed as I press buttons. And I can see exactly what the byte reads. What these numbers are will depend on your board because the controller is built for reading a matrix. Now, what the buttons do will depend on how the manufacturer designed and wired your board. So with this sketch, you can directly see what output you're getting. Now, on your Jetpack cheat sheet, I showed what buttons affect which bits in which byte for the boards provided in my kits. Now, because of the way they designed and wired up the board, it can read multiple buttons at once. So if I press S1 and S5 at the same time, byte 0 will read 17 because both bits 0 and 4 will be high. Also, because of the wiring of this board, all the bits marked with an X will always read 0 because they simply aren't connected to anything. So what you now do with your push button reads is limited only by your creativity. As an example, I have sample code number 2, which is the first sample code, except I ditched the serial monitor. I ditched the serial monitor writing and added some extra lines in the loop function. I declared a new variable called LED array, as I'll need it momentarily. I then set up the board, but I blanked all the LEDs. I blanked out all the LEDs before I turned the display on. I simply put it in sequential addressing mode, set up for a loop right here to blank out all 16 addresses, and then I activated the display and turned it on full brightness. So in the loop function, I used the exact same code and variables to read the push buttons on 4 bytes. I then wrote the individual bits in the LED array variable so that each bit in the variable lines up with the push button. So bit 0, the far right bit in the byte, is push button 8, the far right push button. Bit 7, is the far left bit and is activated by the far left push button number 1. So now that I've got a single byte with 8 bits representing all 8 push buttons, I can set up sequential address writing on the board and use a for loop to write the sequence. I write hex 00 to the 7-segment displays, and then simply read the current bit we're reading in our LED array byte, and sends that value to the discrete LED register. That value will either be a 1 or a 0. So what happens now is pushing a button lights up the corresponding discrete LED. The code is essentially the same to write to the 7-segment displays. Characters you write to an LED do not match their hexadecimal values. For example, if I want to write the character 6 to a 7-segment display, I do not send a hexadecimal value of 6. In fact, I showed that character as one of the examples on the cheat sheet, page 2. To display a 6, I would send a hexadecimal 7D. So if I were to write characters 1 through 8 on the 7-segment displays, I would need a long list of statements checking the individual bits in the LED byte, which then would send a specific hex number to display a specific character. Now, you could do this with an array as well, and I did not get into arrays in Arduino. In any case, it'll take quite a bit of code and basically some character tables to properly display individual numbers on the 7-segment displays. Another project you could do is you could mount this board on the wall outside of your bedroom door. Have the 8 push buttons be a way to enter the top secret code to unlock your bedroom door. You could have your Arduino controlling a servo motor on the inside, which locks or unlocks a latch on your door. Each key press displays the number you pressed in sequence on the 7-segment displays. Type in the right code, it turns the servo motor to the released position and unlocks the door. If you did such a project, you would need to perform a sort of quasi-debouncing of the keys. You see, these push buttons are debounced, but if I hold the button down, every time it goes and reads the keys, it'll read that key as pressed. So you'll want to first register a push button press, but then keep going back and reading the keys until you read that the button has been released. Then you can proceed to read the keys looking for the next button press.